Hi everyone, my name is Yang, and I'm currently an assistant professor at Stanford University in the School of Medicine. It is my great pleasure to be here today to share with you my work. So the clinical problem that I'm interested in solving is the need to stimulate blood vessel growth. And one of the key players in this whole complex process is the production of proteins called angiogenic factors. So why is it important? Well, as you can appreciate, the human body is highly vascularized, and that is because most cell types in our body needs to be able to actually be located within just a few hundred microns near a blood vessel so that they can take up nutrients as well as dumping waste. Also, for a lot of disease conditions such as stroke, heart attack, limb ischemia, or like wound healing such as diabetic ulcers, they're actually caused by loss of blood supply. So if we can develop a therapy to effectively promote the blood vessel to grow back into this tissue area, we can help treat these diseases that affects millions of people. So where are we now? The current therapy usually involves direct delivery of those proteins, the angiogenic factors, or delivering genetic signals that encode those proteins. However, the challenges associated with the current therapy involves the lack of targeted delivery, which may cause undesired side effects, as well as safety concerns, especially associated with the viral-based gene therapy. So how can we overcome this problem? Well, imagine the wound site or the disease site to be our battlefield. And in order to win this battle, if we can send in the right soldiers and load them up with the right backpack and give them a GPS signal so that they know where to go, where to deliver their signals, then the chances that we will win the battle would be much higher. So specifically, in my approach, I have chosen stem cells to be my soldier and load them up with the right therapeutic signals and then send them to the disease site. So specifically from the technical level, how do we do this? Well, I first start with positive charged polymers that we can synthesize in the lab. And these polymers are biodegradable, meaning that they can break down and be absorbed by our body. And upon mixing with the negative charged DNA, which encodes the therapeutic factors, they will automatically condense into nanoparticles, which can be easily uptaken by the stem cells to produce the desired therapeutic factors. So now, taking these programmed stem cells, we can transplant them into the disease site to produce the therapeutic signals in situ, and thereby stimulating the new blood vessel formation. So compared to the current conventional therapy, our approach is potentially much safer because all we need is basically the cells from the patient and biodegradable polymers. It also allows better targeting as well as using the cells themselves as actually a living factory to migrate as well as producing the biological signals in situ. So we believe that this kind of technology platform may have broad impacts for biomedicine, especially in the field of tissue engineering, where people are trying to grow biological replacements for tissues such as heart tissue, nervous tissue, and bone, etc., as well as for treating a broad spectrum of ischemic diseases. You are very welcome to visit our website to learn more about our work, and also send me an email at fanyang@stanford.edu. Thank you very much.